Okay. So the topic of my talk is actually a little bit different from suggestion, but it involves suggestion, and you'll see at about the end of the talk why I am telling this. So the topic of my talk is results diversification, and I guess all of you know what does it mean actually. For instance, you take a query, Vinci, for instance, and you have to guess what's the user intent behind the query Vinci. It has, because the query Vinci has multiple information, say needs behind it. For instance, a user might want to have information on another Vinci, might want to have information on the small village in Tuscany, and so on and so forth. Vinci, the company, and so on and so forth. Obviously, if you submit the query to your favorite search engine, sorry, this should be this, your favorite search engine, then you'll have several results that might be diversified. As you can see, the first one is a company. The second one is the Wikipedia page talking about Leonardo da Vinci. The third one is the I don't know, is a touch screen learning for babies. Anyway, there are many items actually named Da Vinci. And by the way, your search engine is actually the only one among the most popular that are returning this Wikipedia as results. At least for me, I don't know for other people. Anyway, let's get into details. I don't know. Maybe for those of you who have heard about diversification, might have heard that it's basically a coverage problem. Coverage in the computational meaning, the computational problem, coverage, set coverage. Basically, let's see why. Basically, you have a user query, and for each user query, you can tell what's the set of the possible intents behind. So this is mandatory. You have to know what are the possible intents behind the query. Remember this because this is important. So also for each document in the collection, you must know what kind of intents or user intents the document might represent. So a document might be on, for instance, Vinci the company, or Vinci the Leonardo da Vinci, and Vinci the let's say the town in Tuscany. A document might have multiple user intent contained. So to measure the user intent, you need to, let's say, to design a sort of weighting function that, given a document, gives you the weight of each intent for the document. Then having these two, let's say ingredients, you can cast the problem. And basically, you want to select the set of key documents in the collection, obviously, covering the maximum amount of intent weight. That is, you want to maximize the number of satisfied users. So you basically have documents, each of them representing a set of user intent. Then you have a query having multiple user intents behind, and then you want to cover all the user intents of the query with K documents. So you want to maximize this coverage, right? So in the recent past, it has been, several methods has been proposed, in particular IA Select from Agrawal et al. Presented at Wisdom 2009, and an X-Quad presented by Santos, McDonald, and Unis in recent publications in WWDC, IR, and others, are the two most, let's say, representative examples. Both of them adopt this coverage approach. Let's get into some more details. For instance, let's take diversify, which is the problem defined in the Agrawal et al. Paper. Basically, diversify takes as input a parameter k, which is the number of documents you want to have in your result set. So you also take a query queue and a set of documents, which are the results for the query queue, which are generally more than k, obviously. And then you also have a probability distribution, so you have to assume that you have a probability distribution on categories. So basically, for each query, for each category, for each category you can basically say evaluate the probability that category is relevant for that query. Fair enough. So also, as we said before, you assume to have sort of quality values. That is, how much quality a document, in this case, brings to a result set for a query Q and the category C. So basically, it's a sort of it's a sort of weight for the user intent in the document. So basically, you want to find a set of documents, this set S, that basically it is contained obviously in the result set. The cardinality of the document you want to retrieve is K, and this subset of RQ must maximize this function here. And this function here is very easy to understand once you understand it. Basically, you have this V function which measures the probability of a document being relative to the intent C. I recall you that this D is being retrieved for a Q. Then 1 minus this value is the probability that D is not pertinent. Then this product basically measures the probability of not having any document pertinent to the category, and then basically you are done, because here you have that at least one document is pertinent to C. So this is basically the interpretation of this big formula. And you sum up for all the documents, for all the categories. So basically, here you have to select a subset, and then you have to evaluate this function. This probability is the probability of a category being relevant for a query queue. So it's the probability that a category is hidden, say, user intent behind the query. The same for it is known that the previous formulation is NP-hard. Basically, you reduce it from max weight coverage. But the good news is that basically the previous objective function is sum-modular. Sum-modular means basically that if you add an element to the set of results, obviously smaller than k, and let's say if the set of result, sorry, okay. It's quite tricky to explain. So take two subsets of results, as in this case S and T. So suppose that S is smaller than T. If you add an element to S, the utility, the overall, let's say, value of the objective function increases more than if you add the same element to a bigger subset, as in this case T. So basically the marginal utility, let's say, increases, let's say, slowly as the, let's say, result set increases, right? And this is actually a good, let's say, property for a function, because it is well known that functions like this admit let's say, an approximation schema which gives you a 1 minus 1 over E approximation value. So it's quite close to the optimum. Okay? And the algorithm is easy, because given this observation, you basically each time you have to add an element, you add the element, let's say, increasing, let's say, that maximizes the increase in terms of utility or the value of the function. Unfortunately, given that at each step you have to reevaluate let's say, the marginal utility, because the marginal utility depends on the elements you have already inserted. The complexity of this approach is actually quadratic in the number of results you want to generate. The results you have to consider. Okay. Actually, this approach looks reasonable, right? Because you want to cover all the possible query intent, and let's say you can do it using a nice approximation schema, and so on and so forth. Unfortunately, you can think of examples where this kind of let's say, optimizing the function that I've just showed you actually doesn't diversify your result set. Just take this toy example for instance. You have a query returning a result set made up of 3 documents, A, B, C, C, and each document the query in each document can be, let's say, pertaining to only 2 categories, G and H. So basically here you have a table saying how much a document pertains to a given category. So in this case, the document A has probability equal to 1 to pertain to this category. Document B has the same probability to the same category. Document C is actually covering two different categories, the 2 different categories, G and H. So, I mean, if I ask you what's the let's say, what would be the optimum result set for you? What would be the, suppose you want to have 2 results. Obviously, let's say everybody would say that the document C must be there, because document C covers the category H, right? Whereas the other 2 documents don't cover the category H. But it turns out that basically, if you compute if you optimize the previous result function, document A and B are the ones that give you the optimal value, which is 1. Instead, inserting things, if you recall the previous example. Also, X quad diversify, which is the formulation by Santos et others, suffers from the same problem. Let's say the objective function is a little bit different, but the problem is that to compute the objective function, you need to have to know in advance the subset of documents you selected. So basically, you cannot say compute the final value if you don't know it. So starting from this observation, we come up with a very naive approach, but as you'll see, it is indeed naive, but it also gives very good results in terms of effectiveness and, as you'll see, in terms of efficiency. So let's say the idea is the following: suppose you got your query Vinci, for instance, again. Suppose you are able, and we'll see in a while how. Suppose you are able to detect that the query Vinci has 3 different intents behind: Leonardo da Vinci, Vinci Town, and Vinci Group. Right? So suppose you're also able to weight this. I mean, to give a probability for each intent. So these are the probabilities, for instance, for this example. And suppose you have for each document in your result set, you have, let's say, the amount of let's say information content for each of the categories. So for instance, in this case you have half and half a document for Leonardo da Vinci. Here you have a document speaking about Leonardo da Vinci and a little bit of Vinci Town, and so on and so forth. So basically, what we do is to try to, let's say, to push into the problem definition the fact that we want to cover all the three user intents proportionally to their probability. So we want to suppose we want 5 results. Okay, we want to have 5 times 5 divided by 12 results on Leonardo da Vinci, and so on and so forth. So quite easily you select all the documents on this basis. So now what's the difference? So now intuitively the difference is that you don't need to, let's say, know in advance what's a subset of results that you select to understand if your results, if your diversified result set is, let's say, coherent with your probability distribution. In more formally, this is the let's say the formulation. I won't go into the detail. The only thing that you have to, let's say, take care of is the following. Basically, here you have the utility. U is defined as the utility of a result set as a double sum, and the double sum is done on say the probability of being relevant for the query, and also the probability of being relevant, and this is the term that gives you this, for a given let's say for a given query reformulation. Okay, multiplied obviously by the probability of seeing that reformulation. And then we push this constraint into the problem definition. Basically, we want each, let's say, user intent to be represented proportionally to its weight. So basically, we want the cardinality of results for a given user intent being greater than or equal to k times the probability of let's say, of that intent. And then, okay, sorry. And then, why this is better than the previous one in terms of efficiency, obviously. The fact is that if you rearrange, say terms by using a simple arithmetic argument, basically you can say you can obtain this formula, and the only let's say term dependent on the set of diversified results is this one, and also notice that basically this value is maximum when these two values are maximum, in particular and this term is maximum when you pick up those documents maximizing this value here. So basically what you need, the diversification algorithm is the following. Basically you measure this function, and I'm going to give you the meaning in a while. This function is roughly let's say a weight for the utility of a document for a given specialization, for a given query reformulation. So basically you can compute for each document in your result list the utility for each specialization, for each reformulation. Then you sum up obviously for all the possible intent, and then you select, you pick up the top K. So it's basically a sorting on these values. And okay, this is the algorithm basically, and as you can see, say it's not really a sorting, but it's something very similar. We do a sort of heap sort. So we don't want to sort all the n log n, but we want to select all the n elements yielding to an n log n algorithm, but we want to select from the n elements the top k, and as it usual, we adopt a heap-based approach, which has a complexity of, let's say, depending on the number of results you want. So basically, the complexity of this approach is n log squared. Sorry, log k. As opposed to the previous two algorithms that are basically n times k. So we have a logarithmic in terms of k improvement here. So we have to basically fill in two gaps, two details. We have to give three details. Three gaps. The first one is how we can obtain the specialization set, the query. Let's say the set of possible user intents. Basically, we adopted an approach based on query log, and so here is the point that let's say relates this talk to the previous one. So basically, we adopted one of the approaches that we have seen before, or let's say a sort of query suggestion based method to devise possible meanings. That is, for each query, we obtain suggestions for that query, and we, in some sense, we consider those suggestions as the possible meanings behind the query. And okay, this is the algorithm, but the idea is that one. And also, importantly, the probability is obviously the frequency with which say a suggestion is given. So for instance, it's a sort of let me try to. Okay, basically, it's the frequency with which a query is observed in the query log. So basically, here you have the frequency of a suggestion Q prime divided by the sum of all the frequencies of the suggestions you get for query Q. And also, you need to, as I said before, you need to measure how much a result is useful for a given, let's say, specialization, for a given reformulation. And this is the formula. Basically, the formula assumes to have a distance function between two documents. And basically, here you have two results lists, your result list and the result list associated with the query suggested, Q prime. And basically, you in some sense, you want to measure the distance between the document contents in the two results list. And this is basically the formula. So basically, sorry, the similarity between the two lists. So basically, here is the formula, and this factor 1 over rank B prime is basically to demote, let's say to weight less a document appearing in RQ which appears let's say in last positions in specializations probability list, sorry, result list, and then you sum up for all the results in a given specialization. So basically, you measure. The idea is to measure what's the let's say the similarity between the results of your result set and the results of the result set of a query suggestion, weighted by the position of let's say of each document. In our case, we used 1 minus cosine, 1 minus the cosine similarity to weight the say this distance between D and D prime. Okay. So we ran some experiments, basically to devise both the effectiveness and more importantly the let's say the response time, the efficiency of our method. So the first the experiment were run on a standard collection, the track diversification diversity track collection. So basically, we ran the experiment on the clue web B subset of the clue web 09 collection. We took the 50 topics provided by track in 2009. We evaluated the alpha and BCG and IAAP. This is the hardware on which we performed the computation. So. Basically, the first okay. So I don't know if you can read this. I don't think so. But basically, here we compared the three algorithms that I mentioned. So our algorithm against let's say the previous two in the state of the art. And so the first observation, I don't think you can read it, but I can read them for you. Basically. You can see that by varying several parameters, OPT select, which is our heuristic, is always OPER with X squared. Basically, in some cases is also better, but I mean it's not statistically significantly. Statistically significantly better than X squared. It is indeed statistically significantly better than IA select, but anyway. So the first good news is that we don't lose, even using the naive, stupid approach that we let's say designed, we don't lose quality. But the real good news is the following. Basically, this table here represents the, let's say, the time spent in computing the diversified list of results by varying both the number of results retrieved from the underlying search engine. So the cardinality, say, of the RQ set, of the results set for the query Q. And here you vary also K, that is the number of diversified results you want. And basically, as